Hi, my name is Dan, and this video is one in quite a long series of videos that I'm doing charting the progress of creating a simulated 4-bit CPU using DigitalWorks, which is a digital electronic simulation software. There is, in the description below, a roadmap of where we're going in the grand scheme of this set of videos. And a link to the software itself, although you won't be seeing that software in use in this video because this shorter set within the larger set is all about designing the CPU, working out how we're going to put it together. There's a reasonable amount of theory in here, despite the fact that this is actually now quite specific to the CPU that we're creating. And if you try to create a CPU like this in real life, first of all, it'd be quite wasteful, and secondly, we wouldn't be able to do very much because it's only a 4-bit CPU. We've come to the point in our discussion about this where we need to deal with a particular problem that we've got, which is, I kind of hinted at in the last video, which is that some of the instructions that we've got have data attached to them. So these are operations like you want to put a specific value into the A register, or you want to move the contents of the A register into a specific memory location. And so as well as the opcode for this, you need the data. And in other CPUs, when you have the situation, it's actually really common, and a lot of CPUs have a lot more instructions that have data attached to them than we have. But it's quite common for this to be packed into the instruction space. So the first half of your binary number is the is the instruction, and the second half is potentially some data that's been attached to it. But we don't have that. We don't have the space because we've only got 4 bits. There is another way we could approach this. We could put it in the next memory slot. So we could have the instruction in one memory slot and then the data in the next memory slot. And this would be doable. There are a few problems with this. One of them is that we're quite low on memory anyway in the first place. But another is that our fetch then becomes more complicated because we need to be able to fetch the instruction and then fetch the data. And both of these fetch things would use the bus, and so that would be 4 phases instead of 2 phases for fetch. In other places, I kind of accepted wastefulness. In this place, I'm not going to because I do have a solution. And the other issue here is that when we increment, sometimes we'd need to add 2 to the program counter rather than adding 1 because we need to skip over where the data is being held. And in some ways, that's a little bit more complicated, but again, we can avoid this. So what if, instead of packing everything in together, we store the data and the instructions in separate memory? Okay, this might seem like a radical idea. Actually, it's not a new idea. So here's a very high-level look at a thing called the von Neumann architecture. And this is basically where you've got CPU and you've got some memory, and your instructions and your data use the same memory. That's called von Neumann architecture after a guy called von Neumann who presumably invented it. Maybe whilst he was sitting in the bath, maybe sitting outside in an armchair, I don't know. There's another alternative, excuse me, which is fairly well known, not as well known as the von Neumann architecture, which is called the Harvard architecture. And this is where you keep your instructions, your data in different memory, which is kind of, well, in fact, is exactly what I've said we're going to do, but there is going to be a wrinkle to this, okay? So Harvard architecture has 2 separate memory blocks, and you access them separately. In fact, sometimes Harvard can look like this, which is actually that you've got one larger memory block, but you have 2 memory address registers. And so you have one that points to the instruction address and one that points to the data address. Yeah, that can work, but that's not what we're looking for in this situation. And actually, I want to do the opposite, which is what I want to do is I want to use a shared address register which points to 2 different memory stores. And so one of them is going to be the instruction memory, and one of them is going to be the data memory. Okay, so I'm not going to be able to in that sense, access them separately. And it's almost as if I'm just doubling the width of the memory in some way. So instead of having 4-bit memory, I've got 8-bit memory. You could think of it in that way if you liked. And then I'm using half of it for the instruction and half of it for the data. However, because I'm going to be implementing this in the hardware, it is easier to think of it as two separate bits of memory because they're wired up differently. Okay. And in fact, what I'm going to do is I'm going to call this the Northumbria Architecture. So the Harvard Architecture was presumably invented at Harvard University. I work for Northumbria University, so I'm calling it the Northumbria Architecture. It's a modification of the Harvard Architecture. So there are some consequences to this design decision that I've made. Let's run through them. So first of all, we can connect the op register, which is the register that holds the operation, directly to the MDR for the op memory, so with its own bus, um, because the instructions are only ever going to be either in the memory or in that register. So we don't need anything else to have access to them, and the op is going to disambiguize whatever the word is, mediate this. Um, and then that, when you've got a separate bus, that gives us another advantage, which means that we can actually fetch the opcode and the data at the same time, because we've got two different buses. We've got no argument about who's using the bus for this. We can stick the memory address register in once, because it's used for both of these data stores, and we can pull out the opcode and the data at the same time. And the opcode is going to go through its own particular bus, and the data can come through the general bus into the data register. Um, also, as a consequence, we get twice as much memory, which is frankly a huge boost to us because having only 16 locations of memory and having to pack your program into that and any data that you want was very, very restrictive. And doubling that is quite significant. It's still a very limited piece of hardware. But we can do this and make that work for us. And this means that when an instruction doesn't have a data part, that means its counterpart space in the data memory can be used for other data. And we've got instructions for moving numbers into memory. We can use those even when there's an instruction at that location, theoretically, in the way that we think about it. As long as there's no data that's part of that instruction, that gives us that access to that memory as part of it. We don't need to add an extra MAR, a memory address register. So you might say, why not go a little bit further and just have an extra memory address register and do them separately? And the reason behind that decision really is that we're already full with our opcodes. And so if you add another register, you're going to need more opcodes to deal with it or sacrifice some of the ones that we've already got. And actually, the downsides of doing it this way are not huge, and the upsides seem to be quite good, specifically when we're dealing with 4 bits, because I'm not sure that I would approach it in this way if I was going for 8-bit or larger. So yeah, so the fact that we haven't got an extra memory address register means we don't need extra instructions to deal with that. So we can do everything that we want to do within the instruction set that we've already got. But we do need to be careful if we're going to use memory in the data half where there is an opcode. We need to make sure we're not overwriting data that's actually used for the program on those particular opcodes where the data is important, the data half, because that data is inextricably linked, that data slot with the opcode slot, because we're just using the one memory address register, so it accesses both of them at the same time. So kind of quick roundup of these architecture possibilities then. Most computers, as we call them, computers, are von Neumann in architecture. It's regarded to be generally thought of as being simpler and easier to implement, and maybe easier to program for. I don't know, because of the complexities that we've got with this interleaving thing going on. Maybe it just so happens that that's what it is. And a lot of simulators and other things that talk about computer hardware and computer architecture focus on von Neumann. because that is probably the most common, or certainly the most commonly studied. Harvard tends to be used for small, fast embedded processors, so ones that are built into something, particularly ones where speed is of an essence, and they tend to be quite limited processors in other ways. And so is this kind of approach is somewhat suitable for us when we're limited with 4 bits. Um, so yeah, fine. And the Northumbria Architecture, which I've just kind of effectively claimed in this video, may not be new. So I don't know. I haven't done extensive research to see if anybody has actually come up with this particular approach before, but I've not seen it before. So if you know of another name for this Northumbria architecture, please do get in touch with me, and I'd love to hear about it and find out if anybody else has used this sort of approach. If not, I've invented something, and that's great. Okay, so a quick review then of what we've got, or a reminder of how we're going to approach this. We've got a CPU, we've got a single shared memory address register, but we will have 2 memory banks to be able to access. One of which is going to be dedicated to instructions, and the other one which is going to be data memory. And that's it from me for now.